Hello everyone. Today we are going to discuss on multiprocessing and multitasking. Few systems may come up with multiprocessors where it can have multiple CPUs and can be able to execute multiple processes immediately or simultaneously. So the ability to execute multiple processes simultaneously is generally referred as multiprocessing, and system which perform multiple processing simultaneously, we know that ability of a system as multiprocessor systems. And coming to ability of an operating system, which can have multiple programs corresponding to different process in a memory, and these programs which are ready for execution is referred as multiprogramming. In the case of uniprocessor systems, this concept of multiprocessing is does not erase. Let's get into a multitasking. Multitasking refers to a ability of an operating system to hold multiple processes in memory and switch the processor from executing one process to another process. Here we are trying to execute multiple tasks which are right there in the memory waiting for a CPU time. When one of the process gets a time for execution, after a while, if we want the second process to be get executed, then we have to switch process to another process. So switching of execution from one process to another process, it involves contact switching, contact saving, and contact retrieval. The contact switching is nothing but switching of contacts or process uh, from the execution by the CPU. The details of currently executing process supposed to be get saved. So then that point of time, register details, memory details, system resource usage details, and execution details are expected to be saved. So that is nothing but contacts saving supposed to happen before CPU switch its execution from one process to another process. Once the execution is over, or once the switching of the process is over, it will start executing the new process. The moment when the new process execution is over, then to come back to a previous process, we must have to have that detail. So reading that detail is referred as contacts retrieval. Is nothing but it is a process of retrieving the saved contacts detail for a process which is going to be executed due to CPU switching. Based on how exactly the task or process execution switching happens, um, multitasking can be classified into three. The one is cooperative multitasking. Here, in the case of cooperative multitasking, say there are two process or a task which is supposed to be getting executed. So then that point of time, the executing process need not to preempt, continue its execution until and unless it terminates on its own. Or in the case of cooperative multitasking, basically it is most primitive form of multitasking. Why? Because the task or a process which gets a chance to execute only when currently executing task or a process voluntarily relinquishes the CPU. Unless currently executing task relinquishes CPU, the other process or a task won't get the CPU time. Coming to a preemptive multitasking. Here, in the case of preemptive multitasking, it ensures that each and every task or a process gets a chance to execute. When and how purely depends on scheduling algorithm. As the name indicates, In preemptive multitasking, currently running task or a process preempted to give a chance to another task or a process to execute. In the case of non-preemptive multitasking, process or a task which currently given CPU time is allowed to execute until it terminates or enters into a blocked or wait state. Now the question arises, what is the difference between non-preemptive multitasking and the cooperative multitasking? In the case of cooperative multitasking, if currently executing task gets into a blocked state or wait state since it is waiting for some shared resource, then it is not needed to relinquishes the CPU. It may wait for until and unless it gets the response or gets the shared resource. But whereas in the case of non-preemptive multitasking, when the currently executing task gets into a blocked or wait state, it should relinquishes the CPU so that the other process will get the CPU time for the execution. Let's get into a task communication. As we all know, in the case of multiprocessing systems, which is capable of processing multiple tasks or a process simultaneously, in this process, the communication has to establish between multiple processor. So, the processor task running on a OS can be classified like cooperative process or competing process. In the case of cooperating process, here the one process requires the input from the other process to complete its execution. But in the case of competing process, it is not waiting for a response from another process or no input is expected, but these two processes are competing for the same system resource. System resources can be display devices or files. The cooperative process exchange information and communicate among the process by two methods. One is cooperation through sharing, where it exchanges the data through some shared resources, and cooperation through communication, where no data is exchanged or shared, but there is a communication established to achieve the synchronism with respect to execution. So the mechanism through which the task or a process communicate, we generally call that as inter-process communication or task communication. There are multiple IPC to achieve the communication. Let's get into a IPC mechanism. The first which I start discussing is a shared memory. Here, the process 1 and process 2, which are getting the CPU time and current simultaneously executing right now. So the communication between process 1 and process 2 is established through a common memory area shared across process 1 and process 2. So this is the simple method we adopted to achieve communication across multiple processes. So common area of memory been considered to communicate between processes. So, but it purely a kernel dependent, different mechanisms been adopted to implement such technique. That could be pipes or memory mapped object. Let's go into pipes and memory mapped object one after the other. The first method is pipe. Pipes is nothing but it's a section of the shared memory used by the process for communication to establish between the processes. So here it basically follows client server architecture. You can see in the block diagram the process 1 and process 2. Here the process which creates the pipe, we generally call it as pipe server. Process which connects to the pipe is always called as a pipe client. So now uh, these shared memory area which we are calling it as a pipe can be a unidirectional or it can be bidirectional. So if it is a unidirectional, the process can be able to send the data, and the process which connects can read the data. If the pipe is bidirectional, both write and read can be possible at both the ends of the pipe. The creation of pipes or implementation of the pipes is purely operating system dependent. Let's take an example of Microsoft Windows desktop. There are two types of pipes for inter-process communication is established. The first one is anonymous pipes. These are unidirectional pipes, and these anonymous pipes are unnamed. Okay, and it is capable of transferring the data between two processes. And in the case of named pipes, these pipes are named, and these are unidirectional, or it can be a bidirectional pipes. So the process which creates the pipe, we call it as pipe server. The process which connects to this particular pipe, we call it as pipe client. So in the case of named pipes, the process can act both as a server along with it can also act as a client. That means point to point communication can be established by using the named pipes. Along with that, named pipes also can be used for communicating between the process running on the same CPU, or it may connect to a process which are not running on the same CPU. So that is purely depends on what kind of the process and on which platform the process is executing. The next one is memory mapped object. Memory mapped object, basically again it's a shared memory technique adopted by real-time operating systems. Here in this approach, a mapping object is created, and physical storage for it is reserved and committed. So for every process, there will be a virtual space mapped to this particular physical storage. If any process want to share the information, then this mapped object should be mapped to a virtual memory of that particular respective process and can share the data. For more detail, let's get into the detail given in the slide here. Look at the highlighted part of the physical area of the memory. So that is the physical memory allotted for process 1 and process 2, where that entire physical memory area is mapped to a respective virtual memory space of the process 1 and process 2 respectively. So now when process 1 want to write something onto the physical memory, that will be write onto a virtual area that will be mapped to a physical memory shared among the process 1 and process 2, so that process 2 can map that particular respective virtual space of it to a physical memory area given. Let's get into our next IPC mechanism, that is message passing. So message passing is a synchronous or asynchronous information exchange mechanism for interprocess or thread communication. The major difference between shared memory concept and the message passing is that in the case of shared memory, a large portion of the data can be shared across the process, but here in this message passing, very limited amount of information can be passed. Along with that, the message passing relatively fast and free from the concept of synchronization overheads compared to a shared mechanism memory. That means in the shared memory, to have excellent communication, we must have to achieve a synchronization with respect to access to a shared portion of the memory. But in here in the case, there is no such synchronization required to pass the message among the processes. Coming to a different classification of this message passing technique, the first one is message queue, second one is mailbox, and third one is signaling. Let's get into a message queue. Here in this particular concept, the process which wants to talk to another process will post the message in a first in first out register. We call that as a message queue. Here it will stores that particular information temporarily, and it can be read by the other process by accessing to that particular message queue. Messages are sent and received through send and receive methods, where each direction when the data is supposed to be followed, then that point of time the respective process to receive it, that information will be sent through that particular message in the message queue. And the concept of message queue is purely kernel dependent. The second one is mailbox. In the case of mailbox, it is a kind of special type of message queue, where in the message queue we can be able to share multiple data, but in the case of mailbox, it is a simple way of communication across multiple tasks, but it can be able to transfer a single message to a multiple task. For example, the task which wants to share the information will create the mailbox, and the task which needs that information is expected to be subscribed to that mailbox. For example, here task 1 is created the mailbox, and it is broadcasted to a task 2 and task 3 task 4, since task 2 task 3 and task 4 is subscribed to that particular mailbox. During this particular understanding, we must have to remember one thing, that only a single message can be transferred from task 1 to a subscribers, and it is a one-way communication. Next one is signaling. Signals are used for asynchronous notification mechanism. We use the signaling to achieve a synchronization among the multiple executing tasks or a process. Signals do not carry any data and are not queued or stored, and it is purely operating system dependent. The next IPC mechanism is a remote procedural call and sockets. Remote procedural call is the inter-process communication mechanism used by the process to call a procedure of another process running on the same CPU or on the another CPU. RPC is also known as remote invocation or remote method invocation. Here, the process containing the procedure which needs to be invoked, I'm gonna call it as server. The CPU or a process which initiates the RPC request is called as client. In order to make RPC communication compatible across all platforms, these RPCs should stick to a certain standard formats like IDL, interface definition language, which basically defines RPC communication, or Microsoft interface definition language. Basically, this is one of the interface definition language from Microsoft for all Microsoft platforms. And RPC communication can be either synchronous or it can be asynchronous. That purely depends whether it is a blocking or non-blocking type of RPC communication. So here you can see the block diagram, which basically express there are two CPUs and two process. So the process getting connected to another procedure of the process running on the second CPU. So then that point of time we use this kind of communication mechanism. Sockets are basically a logical endpoint in two-way communication. Here we use the sockets for RPC communication. A port associated with the sockets, so that the network layer of communication channel can deliver the data to a designated applications. Otherwise, there can be a mismatch across the line among the process. Sockets are of different types, namely Internet socket, Unix sockets. In the case of Internet sockets, it works on Internet communication protocol. Could be a TCP, IP, or UDP and etc. INET sockets are classified into stream sockets where the connection oriented, and they use a TCP to establish a reliable connection across these particular points. Datagram sockets rely on UDP for establishing connections. Let's get into a task synchronization. As we all know, in the case of multitasking environment, we can be able to execute multiple processes simultaneously. Each time when we execute multiple processes, we use a IPC mechanism to establish the communication across the task or a process. Suppose there is a situation where both the task trying to read and write the shared memory area, then that point of time this will lead to an unexpected results. So to come up with a solution, we comes with a concept called synchronization, where basically it is an act of making the process aware of access of shared resource by each process to avoid a conflict. Why task or a process synchronization is essential? Basically to avoid the conflicts, to ensure the proper sequence of operation, and to establish a proper communication between the process. So the code memory area, which basically holds the program instruction for accessing a shared resource, is known as critical section. In that part of the memory area, we are going to have a instruction corresponding to a access. In order to synchronize the access to a shared resource, it is very important to access to a critical section part of the memory where we stored a instruction corresponding to a accessing to a shared resource must be exclusive, so that the we can be able to achieve synchronism between the two processes with respect to shared resource. Issues to be get considered as far as task communication is synchronization is considered. The first one is racing. Take up a simple example, which is a simple C code. Go through these codes. There are two processes, A and B, has a counter operation to be performed on, and in the main thread we are calling that particular subthread of process A and B in it one after the other. But the simple program statement counter plus plus is like a single statement from high level language point of view in C. But when it comes to a low level point of view, it basically has three different stages. First, it basically loads the counter to accumulator and increment the accumulator value by 1 and stores that particular content of the value from the accumulator with the new count value. So there is three different instruction, low level instruction to be executed. Okay, now the point is, when multiple process are getting executed and these two process A and process B are dealt with the C code right now, as I have shown you in the example. So when it is performing counter plus plus in process A, it basically supposed to execute three lines of code to be executed in lower language. But between the context which happens from process A to a process B, and process B execute the code, and after executing the process B, before it switches its contact, the saved context of the previous process A been retrieved and it will continue its the execution. The problem right now is, during the first execution of the process A, it is about to increment the value of the register, since process B preempted that execution of the process A, and it just performed the one more counter operation on the process B, but it failed to identify that that particular added count in the process A, because the process B is completely unaware on that process A increment of the count by 1. So this problem we referred as racing condition. That is purely because when we convert a higher level language to a low level language, it takes multiple lines of code and the cycle to execute. Let's discuss the second problem, like deadlock. Deadlock is the condition in which process is waiting for a resource held by another process, where the another process is waiting for a resource held by the first process. Let's take an example right now. The process A and process B are considered here. Process A holds a resource X and process B waiting for that resource X. Similar way, the process B holds resource Y, where the resource Y basically required for a process A. So, the both process A and process B can't make any progress, since both the process holding a one resource and waiting for the another. Let's discuss what are the condition favors the deadlock, or what reason cause the deadlock to occur in the task execution. The first point to mention is mutual exclusion. That means this is one of the criteria which basically tells only one process can hold a resource at a time, so that the other can't have access to that particular resource, will leads to a deadlock. The second point, hold and wait. The process can hold a shared resource by acquiring the lock and control the shared access, and it waits for the additional resource held by the another process. Will this also leads the favoring the deadlock. Next one is no resource preemption. That means once the operating system allot the system shared resource to the particular process, unless the process relinquishes that shared resource, operating system can't intervene and preempt the particular acquired process. Coming to a circular wait, this is a very simple condition where let's take the P naught to Pn, P naught, P1, Pn are multiple process right now. P naught is waiting for a resource held by P1, P1 is waiting for a resource held by P naught, and so on. Similar way, it can be of multiple process in a circular manner, holding one shared resource and waiting for another. Handling the deadlock is one of the important jobs to do by the operating system. The first technique is by ignoring the deadlock, we can avoid additional amount or cost put it on to remove the deadlock. But it is not in the case of life critical system where functionalities of that system is so critical. So then that point of time we can't adopt this particular technique. We have to invest our money and time to avoid the deadlock. The one such example is Unix, where operating system follows this particular technique. The next technique is detect and recover. That means in this approach, we simply detect the formation of the deadlock and we'll try to recover it. This is we can take a simple example of traffic junction, okay, where the traffic, once the traffic occurred in that particular junction, we will try to resolve the situation. We will try to ease the situation by making all the vehicle to back up to their position. After that, one lane is allowed to move on. Later, we can find the other vehicles to move, so that the entire junction is free up and deadlock is avoided. We call this particular technique as a backup cars technique, but again, here to perform such operation we use the operating system. It keep the resource graph in their memory, and the deadlock conditions can be detected by analyzing these resource graph by graph analyzer. Once the deadlock condition, if we detect by using a graph analyzer algorithm, the system can terminate the process, or it can preempt the shared resources allotted to a particular process. The next one is avoid deadlocks. Yes, the deadlock can be avoided by careful resource allocation by the operating system. It is nothing but the traffic signaling at the junction. Next one is the prevent deadlock. We can prevent the deadlock by putting the condition saying that no process can request for the shared resource by holding the other shared resources. How do we do that? Yeah, by negating one of the four conditions favoring the deadlock situation. We can prevent the deadlock by putting the rules such as the process must request all the shared system resources at a time, and the operating system can grant the shared resources only when the process is not holding any other resource. The next point in the same is ensuring the resource preemption is possible at operating system level by following the few set of rules, like the first one, release all these resource currently held by the process if request made by the process for new resource is not available. If the process request for the particular process, if it is not available, the resource held by that process should be relinquished immediately so that that can be used by other process. Point number two, add the resource which are preempted or released to a resource list describes the resources which the process requires complete its execution. So that if any process relinquishes the particular resources, that should be listed in a resource list so that it can describe the right there the process required for process which looks for that particular system resource can acquire to that particular resource and execute the particular process code. Coming to our next point, reschedule the process for execution only when the process gets its old resource as well as the new resource which requested by the process. Otherwise, it is not supposed to schedule the process execution by the operating system at the CPU. There are multiple techniques to achieve a task synchronization. Where the important technique we follow is mutual exclusion. Basically, it blocks the process to access the shared resource if the other process is engaging the requested shared resource. So there are two classifications, or there are two ways to achieve the mutual exclusion. One through busy waiting or spin lock, and another by using sleep and wake up technique. Semaphore is a one such example which basically falls on the category of mutual exclusion through sleep and wake up type. Here in this particular case, semaphore is basically a system resource. Once the process which wants to have an access to a shared resource, then that point of time, that shared resource, once it's acquired, before it gets into that, it will acquire a semaphore object indicating that the process is going to engage the shared resource, so that any other process wants to get an access to that particular shared resource, it is indicated that the shared resource is busy, and once it is available, it is going to be get noticed by the operating system. The state of the binary semaphore object, if it is set to a signal, it indicates that the process or thread can access to that particular shared resource. If it is non-signal, it indicates that the particular shared resource is owned by a process or a thread, so that no another process can get an access to a shared resource. Display device and hard disk are the example for exclusive access by the particular process when we have limited number of multiple processes to get access to a shared resource. We can classify semaphores into a binary semaphore and a counting semaphore. In the case of binary semaphore, it implements exclusive access to a shared resource by allocating a resource to a single process. Okay, at a time it only allows only one process to access to a shared resource, and the other has to wait unless the currently executing task relinquishes that particular shared resource. Coming to further detailing on that, let's take an example. The process A can be referred as a man getting into or waiting for a room. So the key act as the mutex object. Unless the mutex object or a key is available, the person can't get into the critical section, shared section of the memory or room. If unless the process A gets that particular mutex, is nothing but shared resource, it can't gets into a execution. So the moment when it gets the mutex, okay, the process will gets into a CPU and it will start executing, and once the execution is over, it releases the mutex object, is nothing but it returns the key, and that key or a mutex can be used by other process, indicating that the shared system resources available for the other process. Let's get into the other type of semaphore, that is the counting semaphore. Basically, it maintains a count between a 0 and a maximum value, and it limits the usage of resource by fixed a number of process or threads. The count basically associated with semaphore object is decremented by 1 when the process acquires the shared resource, and incremented by 1 if relinquishes the shared resource. The state of the counting semaphore object is signaled when the count of the object is greater than 0, and it is non-signaled when the count of the object is equal to 0. And this maintenance of this particular semaphore signaling and non-signaling is purely operating system kernel dependent. The process A wants to get an access to a shared resource. Unless semaphore object is available, it can't get an access to a shared resource. The moment when it is available, it will occupy the shared resource and it will indicate the same. Once the execution is over, it releases the semaphore object and wake up the sleeping process which was waiting for an shared resource. How to choose an RTOS? Decision of choosing a real-time operating system for an embedded system is very crucial, and there are multiple factors which affects the decision with respect to choice of RTOS. We can classify the factors as functional factors and non-functional factors. Let's get into functional requirements, okay, which basically leads to choose a particular operating system as far as functionality of an OS is considered. First one is the processor support. It is not very necessary that all RTOS support all kinds of processor architecture. So, few operating system may support particular architecture of the processor, few may not. So, it is very much have to ensure that the processor we are having should have to support the chosen RTOS. The second one is memory requirements. Of course, the embedded system has its own memory constraints, and it really we have to evaluate to a very minimal ROM and RAM requirements. But taking into a consideration of facilitate memory for an operating system in such a way where we can manage all the constraints of an memory. For example, in the case of a few operating system, ROM memory for holding the operating files, and it stores normally in a non-volatile memory like flash itself. Few operating systems also require working memory RAM for loading operating services. Okay, RAM and ROM both are essential, and we have to keep to a of minimum size. Coming to our real-time capabilities, it is not mandatory that all the operating system we are using for an embedded system supposed to be a real-time. And kernel and interrupt latency. Kernel of an operating system come up with the feature of disabling the interrupt, but it will leads to a interrupt latency. For a good embedded system where a response should be very high, the latency should be a very minimal. Coming to interprocess communication and task synchronization, yes, these two features are operating system dependent. Certain kernels may provide a bunch of options where a few may give a very limited options with respect to IPC as well as task synchronization. And along with that, few operating system offers certain kernel implement policies where it avoids priority inversion. That means there is a concept called priority inversion where the priority of the task being deteriorated for the different reasons. So once the priority is decremented, that leads to a lag in the implementation of an respective process. Modularization support. Most of the operating system provides a bunch of features, but all these features are not required for the particular operation. So, if operating system supports modularization, where very selectively we can pick the essential modules of an operating system and recompile the operating system image for the functionality. Support for networking and communication. Yes, operating system kernel may provide stack implementation and driver support for bunch of communication interfaces and networking. And it also ensures operating system under consideration, which provides support for all the interfaces required for an embedded system to perform the particular functionality. Development language support. Yes, the certain operating system include runtime libraries required for running the applications when codes in a language like Java or C Sharp. In the case of Java, the Java virtual machine customized for operating system, which is essential for running the Java application. Similarly, for a .NET, we have .NET framework. Non-functional requirements. Custom developed or off the shelf. That means that depending on the operating system requirement, it is possible to go with the complete development of an operating system suitable for the embedded system, or we can use an off the shelf. That means readily available operating system can be bought, and or we can use a open source product. We can make changes what we required to adopt it to a particular environment. But it purely depends on what is the development cost, the licensing fees of an operating system, and what is the time or duration given to develop such embedded system. Again, the cost, the total cost of an developing or buying operating system or maintaining it in terms of commercial product or custom build needs to be evaluated before taking the decision on any operating system. So it again purely depends what is the maintenance cost supposed to be for an embedded system. We have to take a decision purely based on cost. Development and debugging tool availability. So the availability of the development and debugging tool is a critical decision making factor in the selection of an operating system design. Certain operating system may superior in performance, but availability of the tools for supporting the development may be limited. Yes, of course, this play a very big role in selecting the operating system. We have to explore the different tools available for the operating system under considerations. Next one is ease of use. Of course, how easy for usage in the commercial RTOS is one of the important factor to be considered. Last one is after sales. Once it is used for the commercial embedded applications, then that point of time how often the bug fixes can be done and the critical patch updates are going to be given. So these things, these kind of support supposed to be given. So even that also going to be get considered when we choose the operating system. So these are the factors which comes in before we take decisions on selection of the operating system.